Welcome back to Applied Physics. In this video, I want to talk about buoyancy. You should already be at least a little bit familiar with the concept of buoyancy as a way of describing whether something is going to sink or float in water or some other liquid. And that's a good starting point, but in this video, I want to try to generalize that a little bit and try to give it a little bit more of a concrete meaning. The theory of buoyancy is going to start with Archimedes' principle, which tells us that an object placed in a fluid appears to lose weight equal to the weight of the fluid displaced by the object. I really wish that I had a practical example here, but unfortunately I cannot safely film it at the moment because it involves spraying water all over the place. But imagine that you had a bowl of water and a rubber ducky floating in your bowl of water. The rubber duck is mostly above the water, but there's this little sliver of duck that is below water. If you take the duck out of the water level will drop just a little bit. Or, looking at it from another direction, let's say that we have a container that is filled to the brim with water. And then let's place our rubber duck in the water. I don't have orange, but let's give him a red beak. When you place the rubber duck in water, it's going to cause some of the water to overflow. So now let's say that we have a second container that the first container is setting in, so that when the water overflows, we can capture it. And then we are somehow able to incredibly carefully remove the rubber duck, remove the bowl full of water, and just analyze this little bit of water that overflowed out of our bowl. It will turn out that the weight of the overflow water is exactly equal to the weight of the duck if the duck is dry. Which is not quite what Archimedes' principle said, but if you stop and think about it, it is an equivalent statement. Most notably, the fact that the duck is going to float. So if we try to draw a free body diagram of our rubber duck, well, we're going to have the force of gravity, which is mass times gravity. And I have to be a little bit more specific here, so this is the mass of the duck times gravity. And there is going to be a buoyancy force pointing upward. And the buoyancy force is going to be the mass of the displaced water. I'll call that m sub w times g. And now we have the equilibrium condition. I said that the duck is floating in the water, which means it is not being pushed upward, it is not being pushed downward. It's sitting at a balance point. And the only way we can have that balance point is if the buoyancy and the weight are equal. So we now have the conclusion that the mass of the water and the mass of the duck are equal. And if two things have the same mass and they are in the same gravitational field, namely the surface of the Earth, then they have the same weight as well. One more experiment related to this, and one that I'm pretty sure that you have done at some point in your life, probably before you entered kindergarten. But if you have a rubber ducky in a bowl of water and you push the rubber ducky down, it will sink in the water. Well, mathematically we could model that, or physically we can model that using a free body diagram where we have, let's see, our rubber ducky course, gravity is still acting on it, and there's still some buoyancy pushing it upward, but now we are adding an extra applied force. And the combination of the applied force and gravity is going to overcome the buoyancy from when it was originally floating. It will still stabilize, right? You push down on the duck, it will sink, and then it will stabilize at the bottom of your finger where you're pushing it under the water. Because as you pushed it down, more water was displaced, increasing the amount of buoyancy. So while you are holding your finger on the duck, it is in equilibrium. And then when you let go of the duck, it's not just going to gently rise up, it is going to pop up and probably pop out of the water and then settle back down. Because as soon as you let go of that applied force, now all of a sudden your buoyancy is quite a bit larger than your gravitational force, causing it to have an upward acceleration. I again apologize. This is something that I'm sure that you've seen at some point in your life, but I would love to be able to show it to you. I was trying to set it up, and I was really afraid that I was going to end up with a computer full of water, so let's avoid the demonstrations for right now. Here's a more practical example. Consider a river barge roughly in the shape of a straight-walled rectangular prism. The deck measures 20 meters by 70 meters, and in dry dock you can measure the outer walls as 0.8 meters tall. How much of the wall will be visible if the barge is on the river and laden with 450,000 kilograms of coal? One thing before we get started that's not immediately clear here in the description, I didn't write this problem, I copied it out of a textbook that is not our usual textbook. Let's assume that that 450,000 kilograms is the coal as well as the mass of the barge itself. I think that's the intention on the problem. I don't think it's phrased in such a way that make that clear, but let's go ahead and assume that. And we know that if we think about this barge, and we think about, the heaps of coal in the barge, that it will float, and part of the barge will be underwater and part of the barge will be above the water. The walls will hopefully be tall enough that it will keep the river out of the barge, and the barge will continue to float on the river even though part of the barge is below the water's surface. Well, to answer this question, we want to establish that we're going to be in equilibrium, which means that the buoyancy force is going to be equal to the weight. And the weight is the mass of the load times gravity, and the buoyancy force is going to be equal to the mass of the displaced water times gravitational acceleration. Mass of the load is given to us as 450,000 kilograms. Gravitational acceleration, of course, is always 9.80 meters per square second, unless we are on the moon or on Mars or in the International Space Station, which are not places that I suspect that we're going to have a barge of coal. And then the other thing that we need is the mass of water, which is not given to us. Although you should know that the density of water is 1,000 kilograms per cubic meter. And of course, mass is equal to density times volume. So mass of water is equal to density of water times the volume of displaced. And we're going to be dealing with a rectangular prism. So we know that the deck size was 20 meters by 70 meters. What we don't know is how much of the barge is going to be submerged. Let's call that little d. And that's interesting to know because the volume of displaced water is going to be equal to the length times the width times that displacement, which means that the mass of the water is going to be density of water times length times width times displacement, which means that the buoyancy force is going to be density of water times length times width times displacement times gravitational acceleration. And that has to be equal to the gravitational force, mass of the load, times gravity. Gravity appears on both sides of the equation, so we can cancel that out. And rearranging this equation a little bit, we get that the depth is going to be the mass of the load divided by the density of water times the length times the width. The mass of the load was 450,000 kilograms. Density of water is 1,000 kilograms per cubic meter. The length, I wrote the length as 20 meters. The width is 70 meters. And if I plug all of that into my calculator, I get that the depth in this case is 0.32. And the units there are in fact meters, which makes sense. We're talking about a length, but it's always worth double checking when you have such a convoluted formula. So in the numerator we had kilograms. In the denominator we had kilograms per cubic meter times meters times meters. These 2 meters will cancel out 2 of the 3 meters down here, which turns this into kilograms over kilogram per meter. Thinking about properties of fractions, this is the same thing as kilograms times meters over kilogram. And now it becomes apparent that the kilograms cancel each other out, and you are left with meters, which is what we had kind of hoped for. There is one more wrinkle in this problem, though. Because if I scroll all the way back up to the statement of the problem, we were asked how much of the wall will be visible. That's this part. We calculated that part. So here's where we use that last piece of information. The walls in total are 0.80 meters tall. So we take the total height, 0.80 meters. We subtract off the amount that is submerged, 0.32 meters, and we get 0.48 meters. A little bit more than half of the wall is still going to be visible above the water. Depending on practical concerns, like how choppy is the water on this particular river, that either means that we have hopefully enough safety factor to prevent the swells from coming over the top of the barge and soaking everything and causing some severe issues, or we could double the amount of coal on this barge and still be perfectly fine. Right? All of those are practical questions well beyond the scope of the problem given to us, so I'm not going to worry about them. I just wanted to mention that There are a lot of interesting questions that could follow from here if we cared. And, well, I have a lot of other stuff to talk about, so I don't care today. One of the things that you should have noticed in this work on buoyancy is that it really depends on having a fixed volume in the thing that is trying to float in your fluid. If that fixed volume displaces enough water that the buoyancy force equals or exceeds its weight, that thing will float. If the buoyancy force exceeds the weight, then it will float with more of it above the water than under the water. But what if you don't have that condition? Consider instead a mixture of two liquids. Oil and water are the classic example. You have probably seen at some point in your life that oil floats on water. That's a very useful property of oil and a good reason for a lot of its usefulness in culinary applications. But how do we know that? We can't talk about the buoyancy force acting on the oil because the oil is, well, it's a fluid. It is shaping to take the shape of its container. We could make this even worse by talking about a gas. Helium gas floats in the atmosphere and escapes to the upper atmosphere, doesn't stay near the surface of the planet, which is very important because breathing helium doesn't help us survive. But we can compress helium to take up whatever volume we want it to. How do we know that it is going to float? And the answer to that is a concept called specific gravity. Despite the fact that I just said we were going to try to look for a way of dealing with things that don't have a well-defined volume or displacement, let's consider a vessel filled with some sort of a fluid. I'll draw it as water, and then some other container submerged inside the fluid. Let's give our fluid a density that I'll call dF, and let's give our submerged container a density that I'm going to call d0. And then let's say that there is some appreciable amount of volume in this container. I'm just going to call it V because variables are going to serve me well today. Well, if the volume of that container is V, then the mass of the fluid that has been displaced is the density of the fluid times V. And of course, the mass of the vessel itself is d0 times V. Then from here, buoyancy force is the weight of the displaced fluid. So that's going to be the mass of the fluid times gravitational acceleration. So that's dF vg. And I'm using the wrong subscript, sorry about that. This is supposed to be F sub b, the buoyancy force. This down here is Fg, the weight of the container itself, d0 Vg. And the interesting thing here is that we want to compare these two values. Well, they both have the exact same volume in the formula, and they both have the exact same gravitational acceleration. So really the only thing that matters is the relative density of the two materials. If you have an object in question that has a lower density than the fluid it is submerged in, it will float. If the object in question has a higher density, it will sink. For practical applications, that's not always interesting because for things like our barge, it didn't have a uniform density in the first place. But for thinking about two fluids mixing together, this becomes a little bit more interesting. For reasons that mostly come down to convenience and historical practice, instead of comparing densities, we tended to compare the specific gravity of the object. And the specific gravity is simply the density of the object, or the density of the material, I guess makes more sense because I'm now talking about oil, not a jar full of oil. So the density of the material divided by the density of water. And really, this is just a unit conversion. The way that I tend to think about specific gravity is that it is measuring the density in units of the density of water. A specific gravity of 1 is an object that has an equal density to water. A specific gravity of 2 means that its density is twice the density of water. If the density of water is 1 gram per milliliter, then these are really easy calculations, but taking away the units makes life a little bit easier when you're trying to work in weird units of measure or you can't agree on what units of measure to use for the problem at hand. Right? The specific gravity of water is 1, no matter if you are using grams per milliliter, kilograms per cubic meter, or pounds per gallon. It doesn't matter, it all works. There is a measuring tool called a hydrometer whose purpose entirely is to figure out the specific gravity of a fluid. So if you have a fluid, we're going to stick this thing, it generally is a long skinny flask with a bulb in it. And then there's some ballast in the bulb, and there are graduated markings going up the side. And depending on how far it sinks, that will let you measure the volume of displaced fluid. You can use that to figure out the buoyancy force. And once you have the buoyancy force, you can figure out what the density of the object is. You can scale that in terms of specific gravity, and you can get a tool for measuring specific gravity. Most textbooks try to teach a hydrometer as doing something very different from trying to measure buoyancy and gravity, but that's all it is. It is a tool for measuring the density of a material in relative terms of the density of water. Because again, the usual purpose of this is if the specific gravity is larger than 1, this material will sink in water. If the specific gravity is less than 1, this material will float in water. So with that little bit of vocabulary, I think this is a good place to wrap the video up. Thank you as always for joining me, and I'll see you next time.